Welcome to HC18. Keynote 2, Collaborative Innovation, a new lever in information technology.
I'm Forrest Basket on the program committee, and I'm here to introduce Bernie Myerson. Bernie is an IBM fellow. He's had many jobs and many titles at IBM over a 26-year career. He's currently VP of Strategic Alliances and Chief Technologist. And before his 26 years at IBM, he actually taught, I think, applied physics at CCNY. Bernie, we're looking forward to a fascinating talk.
Thank you. Let's see if we can find the transfer switch here. There we go. Okay. Well, all right. We've had our first success. This is with technology. You never know. I'll show you some other good stuff later. All right. We've still got people wandering in, so they get to miss the lead-in jokes. From what I hear, by the way, the AV guys assured me the mic was off. Actually, during the pre-session we had down here, what they're going to do for real giggles is just play back the off-the-record conversation. So, when I start this talk, I always ask the same question. The question being, where have all the gigahertz gone? You of all folks should know that this is I can't imagine why somebody would want to take pictures of this. By the way, I should notice if you use a flash, that sucker is white, just little optics. Any case, where have all the gigahertz gone is a very appropriate question, since when was the last time you saw one of those blazing TV commercials we're all so familiar with the new 1.33 gigahertz, everybody'd line up at the store at midnight to get the best one. Those days are gone, and that is a pretty fundamental shift in an industry that's been driven and hyped like that for the last, give or take 30, 40 years, though from what I can see, most of you would be 10 years short of that. Furthermore, it's incredibly logical that I be asking a question in that fashion, given this proximity to San Francisco. And you're going to have to find somebody gray-haired like I am to get an explanation of what the hell I'm talking about. Peter, Paul, Mary, never mind. Okay. Yeah, like I said, 1 out of every 5 people laughed, which tells you where we are in the spectrum. Okay, so let's do a little review here. I should warn you, I used to teach physics for poets, so I developed the nasty habit of digressing. So the talk may be a technical failure, but at least it'll be amusing. Now, it's okay when you know that going in. It's not okay, but never mind. One of the interesting things is we've lived by this rule for years, Moore's Law. And it's probably the most heard and least known law out there. Majority being because most people don't want to go to the microfiche to find the actual copy of the paper. If you actually read the paper, which Gordon, by the way, is quite brilliant, he made a seminal projection saying that, hey, look, every 12, 18 months, sometimes as long as 24, but over a pretty regular period, you're just going to double how much stuff you stuff onto a square centimeter worth of chip. And this will continue to drive economics for the foreseeable future in this industry. And it isn't often people get projections right over 6 orders of magnitude, which is why I refer to Gordon as being quite brilliant. It also, however, speaks only to the density of technology. It doesn't tell you that other alter ego element about performance, and of course, how do you make the stuff twice as dense every 18 months, which would be a really good thing to know, or else you're liable to do something astonishingly stupid. Now, what do I mean by astonishingly foolish is you put 6 orders of magnitude more stuff on a wafer, on a chip, 1 centimeter die. Now, I hope you've all done this back of the envelope. You do understand that if each device uses the same amount of power it did in the prior generation, and you put 6 orders of magnitude more of them on a die, and it was a 10-watt die to begin with, you now have a 10 million watt die. Now that 10 megawatt die in your laptop, when you turn it on, is going to be extraordinarily exciting for a very, very, very short time. After which nobody nearby you will be pleased, you won't really care anymore. So you understand that knowing how it is you make sure you don't immolate yourself when you turn on your laptop, though from what I hear about batteries lately, that's not a guarantee anyway. Sorry, guys. There's going to be somebody. By the way, I count the success of the talk by the length of the hate mail I get at the end. So far, I've got Sony and Dell. The key point here is that there is a rigor to this process. The rigor comes from an interesting guy. Anybody here know who Bob Denard is? Not the guys I spoke with before the talk. Please, somebody tell me they actually know who Bob Denard is. Outstanding. There we go. We got a few live. Excellent. They all also understood the crack about San Francisco and where have all the gigahertz gone. Different generation. Bob Denard invented something I'm absolutely certain you all recognize. You ever hear of memory? Okay. Guy walks into his office one day about 40 years ago, writes down a patent. It's called the single transistor memory cell. That's Bob Denard. Bob has this really cool table. It's about 4 by 4 feet in his office. It's got this really nice rounded pile of metals on it. National Medal of Technology. Nice invention. By the way, we made a few bucks on the patent, too. But one of the other things Bob did was he wrote the counterpart paper to Gordon, which is how you make the transistor smaller without immolating itself. In other words, how do you keep the power density constant? Which is another way of saying if the power that the device used, this 1 square centimeter chip, was, let's say, 10 watts, 6 orders of magnitude of density improvement later, it still burns 10 watts. And there's a recipe. And, it's kind of like the Betty Crocker cookbook for the technologically impaired. It basically says there are a bunch of ratios, gate oxide thickness, diffusion length, substrate doping, you name it. If you maintain the ratios by a set of formulae, lo and behold, you're all set. The next generation will have the same power density as the prior. Okay, so that's all great. The problem is this entire thesis is what the industry has been based on, what progress has been based on for 4 decades. And it failed. It failed in the past, by the way, at about 0.13 microns, several generations ago, interestingly enough. And those who failed to notice that it is now dead had some very exciting times, which I'm sure everybody by now is aware of. When I say it failed, I give a simple example, which is gate oxide. The projections for gate oxide thickness, if you follow the proper rules of scaling, are in fact the lower lines there. I've been told, by the way, not to be a dummy and wave the pointer around at you, so I promise not to do that. And if I do, just yell or duck. I'll notice the ducking. Classical scaling would have said, for instance, the threshold voltage, VDD, in the devices should have followed this trend down as you go to shorter gate lengths. Oxide thickness should have followed this trend, and you have to if you want to obey power density being constant. Funny thing is, the oxide thicknesses hung up, and they actually didn't come down. The reason is really simple. I'll go into that in a moment. But the consequence of violating the rules of scaling is basically that the power density went berserk, which is not a terrible surprise. By the way, to make things really special, I love engineers, man, because, boss, I'm sorry, but I couldn't make the oxide any thinner because the oxide basically failed, right? Just burned out. So what I'm going to do is I'll keep the oxide thicker, but don't worry, because the way I'm going to compensate for the fact that I have a thicker oxide in the device is I'm just going to run VDD a little higher to get a little more performance. Needless to say, that is how you result in your nuclear laptop. Now, the reason for this is simple physics, which is atoms don't scale. This is a fundamental phenomenon. Anybody who tells you that this is optional, we have a workaround, their workaround probably involves nuclear fission. Because, folks, if you got a 5-atom thick gate oxide and you cut it in half for the next generation, that's 2.5 atoms. And when you're working on the half atom, let me know so I can exit the planet. There are people who actually have told me things like this. High K might be a good plan right about now. But the bottom line is, even if you had a 1-atom high defect on each side of a 5-atom thick oxide, this is probably problematic. And you cut the oxide thickness in half, the currents increase factors of 10 to the 3 to 10 to the 6. Anybody here know Alan Fowler? Anybody here ever hear of Alan Fowler? No? Fowler-Nordheim tunneling. Nobody there either. Christ, where are the physicists? Okay, one guy in the back frantically going, I know. Basically, you're at a point where the physics are ugly. Not the physicists, the physics. The point of this is that when the physics get ugly, there aren't a lot of other choices, so you better get real creative. These aren't the only issues. I am sure other people have stood here and told you about these statistical fluctuations, which is another way of saying that when there are exactly 2 dopant atoms involved in setting the threshold of the device, and one of them decides to take a day off, this also could be a problem. Scaling quits. Enough. We've been playing the game forever. It's at an end. Now, the other interesting aspect of this is if you don't believe this, what I want you to do as your homework assignment is go get yourself an 8.5 by 11 sheet of paper and just fold it 10 times, and you just let me know what happens right around the 10th fold. By the way, if you're bigger, meaner, or faster than I am, please don't try this. You'll be up quite a long time trying. Anytime you attempt to do the same thing, which is turn the small knob for 4 decades, you're probably going to get in trouble. All physical systems have their limits. Now, here's the really bad news. We've been there already. The astonishing thing is that those who fail to learn from history are doomed to repeat it. This is history. I proudly put one of the IBM mainframes we had at the top of this chart. That's not good news. On the left side, that is the module heat flux, the heat flux out of the heat spreader in a packaged module. And these were bipolar transistor-based devices. And the funny thing was, during the course of the early mainframe development, for about 20 years, the power per square centimeter out of the modules was about constant. It was a couple of watts. It wasn't bad. You know, the heat sink, 2 watts a square centimeter, something like that. But eventually, it went up a cliff till it reached 13 watts per square centimeter. The reason I do this is not to scare the children, because it's really, of course, at the chip level, you were up around 150 to 200 watts per square centimeter on the die. And the way you cool these things, you took a copper plunger, rammed it down on top of the chip, and ran water across the back of the piece of copper. This was very exciting, particularly when the water failed. Now, what happened is this is an example of already having gone through the cycle of failure. When you scale a bipolar transistor small enough, you turn on new physics, in that case, band-to-band tunneling. And if you get band-to-band tunneling, basically it conducts current roughly as well in one direction as it does in the other, which means you could save a lot of money and just substitute paper clips for the transistors. Unfortunately, it works about as well as a computer. So, the question you got to ask yourself is, well, how bad is it? 13 watts per square centimeter. Let me give you a reference, right? If you iron your pants, that's 5 watts a square centimeter. So please, don't tell me, hell, I got a 13-watt bulb, because if you think that's funny, put your hand on the bulb, plug it in the wall, and just stay there for a while. We'll talk. So what do we do? Well, in probably what I would argue is the gutsiest move, certainly in the history of our company, a bunch of guys said, folks, bipolars had it. And a couple of years before this disaster, because they do have very good headlights, I mean, you have a research division for this reason, basically people had worked frantically on alternatives, one of which was, of course, CMOS technology. The stuff at that time they made singing birthday cards out of. However, although it lacked performance, good Lord, you could integrate the bejesus out of it. And of course, we jumped off the curve and got down onto the lower one. All's good in the world. But again, the engineering community is a wonderful thing. You see, because we got near fatal trouble by overscaling bipolar, we have now a model we can follow, so we overscaled CMOS just to be sure. I actually was standing in front of an audience of about 20,000 people when I first showed this slide, and it dawned on me how unbelievably stupid that looks. And so I thought about it. I said, my only explanation, if you're a hardcore engineer and your hand is in the door and the door slams on your hand and breaks 3 fingers, what you do is you put your elbow in, you pry the door open, you put your other hand in and slam it to get a second data point. I proudly point out the points on the top right side of that curve are not ours. Okay, we actually, one hand was enough. We're not going for 2. But you do by the way, those were desktops. So it was great. You ever wonder all that rash of thefts of helicopters to bolt them to the heat sink? This caused a real problem, needless to say, because there is no other technology, folks. We ain't jumping off to make our indium phosphide computers. Both those transistors are going to work really well, but the integration levels required to make anything of interest exclude any of the materials we have today, probably for the next 2-3 decades. It's not to say there won't be alternatives. It just says they ain't here now. So now, this is how you know you've gone over to the dark side, your executive management. You say, this is an opportunity for innovation. If you're the engineer in charge of the next project, you say, oh, God, and other unprintables. So there has been a discontinuity. Like it or not, I actually said this, and this is great. People used to throw eggs at this. I showed this 4 years ago, the very first part of this pitch. And it's kind of interesting. When you tell people the world is ending, they kind of laugh right until something lands on them. But at this point, I don't think there's a lot of debate, which is in the past, scaling is how you drove performance. The interesting thing is in the future, it's going to be innovation. Just making things smaller doesn't work. It doesn't. It stopped working. You have to decouple some of the physical phenomena in order to make progress. In the past, the statement of, by the way, that has nothing to do with Moore's law. Classical scaling is not Moore's law. Moore's law is the second one, which is scaling drove down cost, and guess what? It will still. No kidding, right? If you can make it smaller, and if you can make it, smaller more cheaply, quote unquote, in terms of areal size, you win. So it's not that Moore's law ends. You will continue to make things smaller because of the economics of the business. It just it's irrelevant. Performance used to constrain us, and interestingly, it's now power. And that is at many levels. It's not just about setting fire to your lap. It's setting fire to the data center. It's having the guys from the power company come down and just laugh when you tell them what your electrical requirements are going to be, or the air conditioning guy coming by to see why you set fire to the heat exchanger. These are not little problems. Active power used to dominate. Nowadays, the interesting thing is the devices, when they get small enough, they actually burn, percentage-wise, more power when they're doing absolutely nothing. It's kind of like a teenager. Yeah, that'll get home to my daughter, and I'm a dead man. The focus used to be on processor performance. Everybody says, give me more megahertz, give me more gigahertz. Now they just say it hurts. I mean, they don't want any more of this. They've had enough, thank you. What they really want to do is, system. When was the last time you ever saw somebody, take a chip in their hand and go, oh man, that's good? If I ever encountered somebody, my first step would be to take 2 steps back. I mean, this is not relevant. The chip is irrelevant. It's the system that a customer buys. You probably want to think, therefore, a little more holistically than I got the world's best chip. I know this may not be the conference to say that at, but I'm faster than you are out the door and it's locked. Okay. So what do you do? Going forward, there are many areas you focus on for innovation: materials, structures, processes. And no, I'm not going to cover these in detail. Don't sweat it. Basically, there's actually a long history of materials already driving dramatic improvements, just nothing as seminal as we need now. We've done silicon, germanium, and copper, and silicon and insulator, low-K, strained silicon. And it's getting more and more interesting. I mean, strained silicon's a great example of where physics basically now drives process instead of scaling. At a fixed dimension, if you take a tablecloth and you yank on the 4 corners, basically if you then take a piece of silicon and do the same thing, which is a neat trick, but you can, what happens is when you stretch silicon, as you know, you break a degeneracy in the conduction band, you get light electrons as the dominant carriers, and lo and behold, the electron mobility soars. And I don't mean a little bit. If you measure it at 4 degrees Kelvin, the best number that was gotten before we started this work back in the late 80s, people had 2,000 centimeters squared per volt second was kind of the upper bound on electron mobility. When we got done with the work, early 90s, showing you could do this, the record was 750,000. So from 2,000 to 750,000 demonstrates you might be onto something. By 2001, this is in every device out there that we ship. And in fact, interestingly, if you have the Xbox 360s, where we build the processors, you'll find that dual strain liners where you squeeze PFETs to make them faster, stretch NFETs. God has a sense of humor. They couldn't both go the same way, right? But the fact of the matter is, it can be done, and it's done commercially. And all you have to do is squeeze all 500 million transistors one way and stretch the other 500 million the other way, and it works fine. So, and it actually did work, which is astounding. And yes, somewhere out in the distance, you can do carbon nanotube FETs. However, not in any time frame that's going to help us out of the current conundrum. So there is a device roadmap, but it's innovation and not extrapolation that's critical. And that's an important message, folks. The easy days are over, which is really, there was a time when we really thought this would go on forever, and for good reason. People used to predict lithography would die at 2 microns, and then at 1 micron, then half a micron, then a quarter micron, then they finally realized, well, you've been wrong 10 times, quit now. The key point is this is simple physics. This isn't like, atoms don't subdivide. I don't know how else to make it any simpler than that. So people have come up with very clever ways, finally, of dealing with these at the materials level. But there's a lot of other things you can do. Now, holistic design is what I was referring to earlier when I said, you don't just grab the chip and gee, how exciting that is. Holistic design basically is the argument that if you optimize from the level of the materials to the devices, to the circuits, to the cores, to the chips, through the system architecture, take all the assets into account through virtualization, use system software to simultaneously keep everything in harmony, you can get multiplicative benefit as opposed to percentage benefit. You got to remember that, 1.33 to 1.66 was the big jump in frequency. That's a joke. That is a joke on the scale of progress. Does anybody know or have any feeling for if, let's say, frequency is going up at 15, 20% a year historically? Compared to that, how fast has IT performance gone up a year? Anybody have a feeling for that? Yeah, nice to know you guys are insubstantial, you know. The performance goes up like 90% a year and clock's going up 15. Gee, you know, somebody else, maybe the software guys are actually contributing something for a change. The key is all of the attributes of the system working together, again, give you multiplicative benefit. And this is what provides the actual power in the future. It's not that the chip doesn't matter, not at all. What it means is you have to engineer the chip to take full advantage of all the other system assets. So this is actually a foil I showed in Microprocessor Forum 2004, which I got a raft of hate mails for predicting this phenomena. And I will tell you that what's kind of fun is back then, committed in 2005 to 2007, we'd have 2 new sets of cores that, unlike the prior cores, would nonetheless, they would use all sorts of tricks. But at the end of the day, despite my prediction of falling off the frequency curve, they would continue up the curve, and in fact, they did. So it's not even that the world is over. But I will tell you, the way we drove them up the frequency curve was through innovation, not just through rigorous scaling of the transistors. It doesn't work anymore. And basically, what my message at that time had been is, don't bet against technologists. The engineers in this business are incredibly clever. And there are ways around these issues. And I'll talk about some of them now. I mean, just think about, by the way, that chip that's 4 to 5 gig, that's our Power 6. That thing is actually huge. I mean, it's a Frisbee. The thing is, roughly approaching 4 square centimeters. But the interesting, how do you clock something at 5 gig when it's 4 centimeters squared? Do the math on the speed of light across the chip. The clock tree alone is a work of art, but it can be done. They're just incredible system challenges. It's not brute force technology that'll get you there. Now, remember I talked about multiplicative effects. Again, virtualization. I know I apologize. I'm going to talk a little bit about software here. But virtualization, where you take all the system assets and use them in a somewhat more clever way at the level of the system, provide enormous benefit. I'll give you a simple example. When you have a core, such as one of the earlier ones I showed there, when you have a core such as, let's say, a Power 5, not a dual core. I mean, dual cores have been around since we were shipping them in '01. I'm talking about something where, for instance, in Power 5, you've gone to whole new lengths, such as, for instance, micro-partitioning, where it's a dual-threaded core, but you can actually partition each of the threads 10 different ways. So effectively, you can partition that chip's function 20 ways, the processor. When you can do that, what you do in virtualization is you create little software proxies for each one of those 5% subsets of the capability of the chip. You dump it all in a bucket. So you've got a hypervisor that's looking at the incoming workload and says, geez, somebody's sitting at the screen typing in 18924, which is the passcode to their bank account. And you're supposed to mask that typed passcode in a transaction against the stored passcode to make sure they're actually who they say they are. This does not require rocket science computational capability. So as a consequence, it assembles a virtual machine from the smallest unit of proxy for each element of the system, the smallest unit of memory, smallest computational unit, which is only 5% of the core, and so on, and it does the computation. While it is doing that, what it's just done is given you a 20-fold increase in the capability of dealing with those transactions, because the other literal 19/20ths of that core are available to do the same thing. If you didn't have virtualization, they wouldn't be. So you pick up 20x in the performance of the system just by a software trick. Now, virtualization's been around a long time, but it's becoming vastly more sophisticated. So again, this is why it's not just about clock and not just about chips, but it's how the chip interacts. It wouldn't be possible if the chip hadn't been micro-partitioned, but it also wouldn't be possible if the guys who did it hadn't talked to the guys running the virtualization engine that actually does the partitioning. Similarly, you can also design unbelievably integrated processors where you take the whole system and put it up on the chip, and I'll show some more detail on these. And it doesn't matter whether you're talking about the cell processor, which is just a multi-core, one controlling processor, 8 SPEs, synergistic processors, or putting security cores within a major core, or Blue Gene, which is kind of interesting because it's somewhat Neanderthal technology in the world's fastest supercomputer. These are Power 440 cores that have been around years. They 800 megahertz, 800 megahertz clock in the first Blue Gene, and it blew away anything ever built because of massive parallelism. system on a chip approaches, basically, actually, again, by factors. And I'll give you some scope for those factors. In Blue Gene, basically, it was a scale-out. The Blue Gene core is interesting. It only has 2 processors on it. And that 2-processor core, which is blown up a little bit on the screen here, I don't know how visible it'll be. All you've got is basically 2 processors sitting there, shared memory, and all the rest of this is basically 5 different communication networks. Why do you need 5 networks? Well, if you're going to have 100,000 processors working simultaneously, you need networks with highly disparate characteristics. One network has a bandwidth of 0. It can transmit essentially no bits. However, the latency is also 0. So all it can do is scream, stop. Really good thing to actually have in a large machine if you want to ever have things happen in any kind of order. Similarly, though, it also has to have a network that has seemingly infinite bandwidth. You don't really care about latency because you're writing to a disk drive. So the point is that diversity of design, that systematic approach to designing the chip can many times have much more impact than even the technology it's built in. To put a number on that or a point on the exercise, when this thing was introduced, when Blue Gene was originally introduced, it actually outran the prior 3-year-old mark by the Earth simulator by 20%, 10%. It wasn't a big win, but it was nonetheless the world's fastest supercomputer. Everybody got very excited. They completely missed the point. That was, in my view, irrelevant. What is relevant is Blue Gene was 100 times smaller than the preceding machine. It was a 100x improvement in size, and it burned 2,800% less power to outrun the prior machine. And it was built in an older technology. That's a hell of an achievement. Again, holistic design. Somebody actually thought about the system you wanted to produce when building the actual underlying processors and chips. Same thing with scale out now at the chip level. People have heard over and over again about the cell processor, and it's a tremendous achievement. I mean, it is kind of interesting. If we were completely shameless, like I have certainly met several people who are, we might have considered taking 4 of these things, you put it on a single die, you can get 4 of them to yield. The yields are very good. You could easily get 4 working. And then what you could do is take this thing and you could plug it on a board and say, I have the world's first teraflop chip. Teraflop. It works. It's over 250 million, 256 gigaflop each. So it is a fairly impressive outcome. But it's hard to really appreciate how powerful these application-specific processors can be until you see it visually. So I'm going to show you a couple of interesting ones here. OK. This is a vanilla x86 system attempting to run a program called Terrigen, which is a terrain rendering engine that you need to run within the actual systems that produce the graphics, such as for the Sony PlayStation. And what you'll see is in a conventional Intel workstation, I'm going to kill it, because after about 2.5 minutes of frantically trying to render the first frame, it dies. So you never actually get to see what the first frame should look like. Nonetheless, this is sort of the benchmark for a nominal system. At the time this work was done, this was revealed about a year back. Now let me go to the next demo. All right, this is, again, top of the line, dual core G5, fastest video system certainly out there. And basically, that's what it should have looked like after the first frame was drawn. And it can render the thing at the rate of about 1 a second, best case. So there you go. That's very exciting. Now we're going to show you an undocumented feature of Microsoft. I'm going to go ahead to the next slide, and it's going to freeze. I'm going to then go back twice to the previous slide, then go forward once, called the Microsoft two-step, and there it is. We've been doing this for a year. I have had nobody, if anybody knows why the hell that is, feel free to come let me know. I haven't got a clue. However, that is actually what it should have looked like. You will notice that, by the way, is being run on a cell chip, only using a couple of the SPEs. It isn't even breathing hard. This is not the full chip. The interesting thing about it is you show this to audiences before, not after lunch. Some people do not react well. I suggest those of you who are not having a good reaction either move from behind the person in front of you or don't look. So in any case, I actually have a friend, by the way, who flies like this. I don't fly with her. The point is, this is actually why you build these specialty processors, where you've built the processor with the application in mind. Holistic design. You actually sit down and say, I'm not going to build the world's most mediocre general processor. I'm going to build something that just is extraordinary at one thing. That doesn't say it's an end-all, be-all. There are other things you want to do. But you know, there's a whole industry out there in this space, so this made a lot of sense, and it's turning out to be a huge win. It's not all fun and games. You know, we always love to show this because you want to be a hero with your kids, right? Be the guy who walks through the door with the first Microsoft Xbox 360 or the first PlayStation. Either way, you're kind of a winner. But there are a couple of other more serious things you ever do. You know, I'm sure somebody in this audience, anybody here ever have an MRI? Oh, yeah. It's great. I ask who Bob Denard is, I get no answers. I ask about MRI, half the place says, yeah, me. Some with both hands. I assume that means twice. The interesting thing about it is, if you try to render the video on a high-speed workstation, this is roughly what you get, which is generally why people take an MRI and then you come back the next day to have it read. It's kind of hard to do this stuff in real time. One of the companies we work with said, geez, you know, I know how to, by the way, the amount of data is frightening that these things generate. But he said, no, I know how to handle this. You just run it through one of these, run it through a cell device, run all 8 SPs at full flog, and because of the way they're architected, you get a slightly different result, which is this. So the rendering of the entire MRI took 2.02 seconds as opposed to about 20 minutes. The acceleration factors are pretty damn amazing. You don't want to think, by the way, that's a real person. That's a very personal look, so we'll just go on. And I'm sure I violated several privacy laws there, but the person doesn't know, so what the hell. That's at the level, you know, of application-specific systems, but sometimes the environment is heterogeneous. It's the same thought. In a holistic design, what you do is you say, look, you know, what are we going to be doing out there? Well, we're running DB2. There's a whole bunch of Java apps, and so on and so forth. We need security engines. So whether you're in a mainframe, one of our power systems, Blade Center, you can design a heterogeneous approach to it where, OK, fine, combine the assets. If you look at blades, you got blades that are designed for everything from basically running power to running on x86, running AIX, running Microsoft Windows. It doesn't matter, running, you know, transaction processing, doing voice over IP, communications blades. The point is the world you know, you're moving towards, again, a system focus. But it's not to say the underlying technology is unimportant. It's to say you have to align it with the ultimate application. Similarly, this is another very important thing, collaboration. A decision was made years ago that IBM would basically be part of the open community. You know, you can either try to do everything proprietary, but then you take the risk that you're assuming you're actually smarter than everybody else in the world, which I have found not to be the case, at least in personal experience. Those of you who still believe that, don't raise your hands. You'll get a lot of laughter. The fact of the matter is, the organizations, whether it's blade.org or power.org or J2EE or you name it, you know, these basically are an incredibly rich environment for collaborative progress. And collaborative progress from our experience has been hugely valuable to the company, both financially, technically, and frankly, culturally. Now, a couple of other interesting problems that have cropped up along the way. I added this material, so you're not going to find this particular one in your, this is just one foil, 2 foils, in your book, but I thought it was appropriate because it gets people's attention. I know several people whose attention it really got. So here's an interesting curve. Pun on, I apologize already for the hot button, you know, wisecrack. Basically, there's an interesting set of numbers here I want you to just look at and tell me what's wrong with this picture. So in green is the cost of powering and cooling the server base out there. That's the green. Below it is the spending on server purchases. Does this bother you? Isn't that interesting? Actually, I know somebody who looked at this and was really confused by it. I'm still trying to explain that, guys, it's not not rocket science. Lots of servers being put in use, not a lot being taken out of use. So while the amount you spend on buying new servers is relatively flat, this is cumulative. Oh, man. So I ask you, where do you think your CFO and CIO are going to butt heads? Somewhere's right around here. And this is interesting, again, because guess what? 2007 is the year it hits the fan. It's terrific. You're here right on time. So those of you who've made your specialization in cooling and reducing power use in servers, good for you. I will point out, however, those of you who are making a living out of reducing power in the chips themselves, well, that's just a piece of the puzzle. That ain't the whole story. Actually, it's not even close. But this is a startling thing, because think about it. In 2000, think how the world has changed. Back in 2000, all anybody gave a damn about is give me horsepower, right? Give me more servers. I got to handle the load. You know, I'll plug it in, right? We take it for granted. We've been trained all our lives. You stuff it in the rack and plug it in. Nuclear meltdown never occurred to us. Nowadays, basically, you can't plug it in. If you plug it in, you're going to wind up with the data center operators medium rare. It just doesn't work anymore. So you have more of a problem deploying the things in terms of supplying power and cooling them than you actually have buying them. Now, systems are one of the three issues, right? The issues you have are systems, racks, and the data center itself. This is great. I can lean into the mic and deafen everyone. The interesting thing is, again, even at the server level, just the actual unit, the 1U rack, the power supplies, they themselves are a bizarre issue. People hadn't paid attention, right? What the hell? It's a power supply. Who cares? The original power supplies typically people are using, and most of them are in use today, are like this. They're only 70% efficient. And by the way, the systems run on DC. Yeah, so you start with AC. You're going from AC to DC, you put 1,000 watts in, you were getting 700 watts out, the other 30 watts. The 300 watts will waste heat. So you were already 300 watts of waste heat before you even turned the damn thing on. Then you go ahead and you ignore that at your own peril. So one of the things we spent a lot of time doing is really boring stuff, like working on efficient power supplies, which are now 90% efficient. So you put 1,000 watts in, and lo and behold, you get 900 watts that are useful, and only 100 watts of waste heat. Okay, huge win. Nobody pays attention. And the reason they don't pay attention is people didn't look ahead in the financials and realize this is going to crater the industry if we don't do something about it. Now, there's something else, and I always enjoy this because this is so trivial it's almost funny. The guys, by the way, who invented this are going to lynch me when I get back. But do you realize that, a typical server, you do know how this works, right? You blow cold air in one side, you blow hot air out the back, suck it up into the air conditioner, and you hope that it gets cooled. And of course, some of it recirculates at the top, which is why in most good server racks, the one on top is called the condemned server. The top 5 servers basically get baked to oblivion. The other thing you should know about this is air is a really, really crappy cooling fluid. I mean, folks, you're scientists, engineers, you probably know the specific heat of air is a little worse than water. Or putting it for those of you who haven't had that level of training, let me ask you this question. When you want to cool off, do you dive into A pool of water, or B, a pool of air? Okay, if you dive into the pool of air, the landing sucks and it doesn't cool you off. Okay, so you understand, this isn't rocket science, and yet for some reason, as clever engineers, we've all decided that we're going to cool these things with air, and this is good news. Maybe not. Now, if you want to go back to the future, what you get to do is you say, Jesus, you ever heard of something called a radiator? They've had them for a while. What would happen if you just took one of these stupid things and clamped it to the back of the rack? So instead of blowing the hot air freely into the room where you then have to pipe it through God knows how much building, heating, by the way, the building the entire way before it finally gets to the heat exchanger, what if you just blew it through a heat exchanger on the back door and pulled out more than 50% of that heat and just ran it down a pipe into the floor, which you then ran off as water? It's a water-cooled heat exchanger. Well, that's rocket science. Well, if you did that, a funny thing about it is the cost of doing it this way is, give or take, about 1/4, 400% less expensive than using air. Now, I'm not suggesting we go back to water cooling, copper plungers on chips. We're not that desperate yet. But this isn't rocket science, and it's a big issue. In fact, it's, by the way, that actually is the product. And these things are actually very inexpensive. But there's a culture. We all grew up when water cooling was a dirty word. The big achievement was air cooling. It hasn't dawned on anybody that you ever drive a car, open the hood, take a look up front. You'll find several different radiators. I haven't lost one of them in many, many years, except when you modify the length of the car, and that's a different issue. Now, here's the economics. And again, they're fairly startling. So take a look, if you would, at an air-cooled server rack. This is the load. The red section is how much of the electrical power sucked into that rack in kilowatts is actually used doing anything useful. And it's about, 46%. Now that's kind of interesting. In other words, you throw away the majority of the energy doing nothing to do with actually computing, and you spend it on a lot of other things, like lighting and office space conditioning, electrical room cooling, plus the cooling tower itself, and this huge, huge blue chunk, which is damn near the size of the red, is what the data center cooling is costing you in terms of electrical consumption. That's it's fairly frightening. If you look at a water-cooled server rack, what happens is, in fact, since you're removing way more than half the energy in just a water-cooled system, in fact, you're down to only about 15% versus 30% of the energy spent on cooling. Furthermore, the interesting thing is the cooling tower plant, it doubles, goes from 2.5 to 4.5% consumption, which is nothing, because water is an incredibly efficient cooling fluid. This should not be news to anyone, but when I show people this, they sort of scratch their heads. And the wonderful part about this, by the way, is now at least 56% of what you're spending on energy is being spent doing actual work as opposed to only 40-something%. So again, these aren't little issues, and sometimes they're addressed by relatively seemingly fairly straightforward things. You can get much fancier than this. This is just the point that even in calculating how you set up a data center, the tools have become incredibly sophisticated, where last week, in fact, we commercially deployed a series of finite element analyses you'd normally find in an advanced physics lab that actually look at the airflow in the cool data center. And in fact, this is why you're immolating the top servers, because as the heat exhausts, some part of that heat wraps around in the front end. These are the airflow patterns that produce that, and if you water cool, that whole problem goes away. The other thing is kind of interesting. I actually watched somebody design a data center, and it can also get fairly funny. What they did was they read the label on every device in the data center, added them up, and designed it to cool that. And they had something called a sub-zero freezer. Anybody know, or let me put it a different way. Did you know that about, 15% is the nominal utilization of an x86 server system? About 15%. Don't even think what the utilization is of your desktop. That's almost funny. That's single digit. So, I know you want to talk about global warming, shoot all the engineers. What can I say? It's quite serious. Actually, we can't do that because now it's all PDAs, and we're back down to milliwatts. The bottom line to all of this is that there's a huge level of sophistication needed in the power area, which currently isn't there. So it is one of the next big challenges. Now, here's another very useful piece of information. The bottom line is, this is the utilization of a server body this particular example is drawn from our blade centers. This is the AC power, and the funny thing is, if you're at 25% utilization of blade center, you're pulling about 1,250 watts, and this is pretty typical of any system. The nice thing is, if you increase the utilization from 25 to 75%, which you can do through virtualization, basically, you only increase the power consumption about 50%. So in other words, you get 300% the performance for 50% more power if you drive the utilization up. Again, why is micropartitioning important? Why is virtualization important? Because you need to move to the far right side of the curve so you dramatically improve the IT performance. So again, I know I'm beating this to death, but if you don't have a holistic view of the world, if you don't look at the system level and the consequences of what you're doing there, you'll never build the elements correctly. Now, here's another little piece of, I think a plug for what I call collaborative innovation, which is you wouldn't believe what this sort of innovation costs. I'm using the instance of silicon technology since it does have some impact on your lives. Whether you're doing changes of litho from dry to immersion, going from silicon to strained silicon to high K, dual gates, your interconnects going from aluminum to copper, then low K, ultra low K, all the other good stuff you do. When you do that, a funny thing happens. I took out the other data. This is from a friend of mine, Dan Hutchison at VLSI Research. I replotted his data. So I took the ratio of the revenue you get for every dollar you spent in research and development in a given year. It's not quite right because there's an offset between the two, but it's close enough for argument's sake. And a funny thing happens on the way to actually surviving, which is you don't. You see, in 1955, for every dollar, somebody owns a fab out there, for every dollar you put in, you get back about 55 bucks if you go back to the early days. Then you go to 1980, and for every dollar you spend in R&D, you get back about $20 of revenue, which is actually pretty damn good. Then you get to the year 2000, and for every dollar you spend, you get back about $6 of revenue. Okay, let me give you some perspective. That means you're making 16% PTI, right? 16% profit, and then taking 100% of your profit and shoving it into R&D just to break even, which really aggravates your shareholders. This is a non-starter. This is an industry that is following a trend that is neither sustainable nor, in fact, in any way acceptable. So it won't work. And there are only two solutions you've got. The solutions are you either increase your revenue for a fixed investment or you find a way to share your investments, so for a fixed revenue, you actually get a better result. In other words, you don't have to invest as much. The only way of doing that is collaborative innovation. And what's happened is it's already gone on. In our industry, we are globalized. You know, people always talk to me, you know, about, oh my God, you're outsourcing, you're moving things overseas. It's funny, you know, good Lord, yes, we also have a huge amount of our development here, but people forget IBM, you know, the first word is I, international, been there for about 50 years. It's not news to us. But the globalization of this industry is incredibly important because it's not just about taking and globalizing it for the sake of sharing your capital investments, but it's your intellectual capital as well. When you share the capital, physical, and your intellectual capital as well, you wouldn't believe the efficacy of the efforts that you can actually derive from that. And we basically do it, as do a number of other companies, for the purposes of basically what we call coopetition, you know, pre-competitive investment. We're going to go compete with each other later on in the cycle of developing systems and IT solutions, but at least here, we've given everybody a chance to participate in the industry. So, you know, there are a lot of levers currently out there that people are beginning to pull that are new ones in this business. For instance, innovation and integration are now delivering what scaling no longer does. You can get high-frequency systems out there. They do work, but they took a lot of innovation, and they work via holistic design. Thermal issues, which were already critical, are just going to get worse, so there's the good news, because now we have future employment for everybody in the auditorium. System solutions are going to dominate progress. You know, the progress in technology is going to be in percentages, and system solutions will be in multiples. Fiscal reality, however, is driving towards consolidation about innovation networks, which is why we believe in open as a strategy. And the last thing is collaborative innovation. That is a key strategic imperative. You know, whether that's the industry getting together under the aegis of the SIA and collaborating there, or companies getting together openly like this, at the end of the day, this is what, you know, is going to drive our survival in the future. So on that note, and mercifully so, I'm done. Thank you.
So thanks, Bernie. That was terrific. We have time for a couple of questions.
Bernie, it's Dean Takahashi at the San Jose Mercury News. Was that a picture of Project Gotham Racing 3 with the secure blue little tag you had? And so does that mean that the secure blue technology is used in the Xbox 360?
No, it's just if you think about gaming as an example of where, you know, security is a nightmare, think about a network, for instance, where you had to transmit data. For instance, you wanted to actually do it online. For instance, you wave your cell phone at a, at a vending machine. Kind of great, right? You wave your cell phone at a vending machine and it spits Coke at you. However, it does, at the edge of that system, capture all your ID and ship it back over a network that could be 5,000 miles to your home bank and withdraw money from your account. You probably, at every node there, would like heavy-duty encryption and, oh God, you know, don't lift all of my information.
Okay.
Hi. You talked about the need to move towards collaborative R&D, I think. In that case, how do you decide on how the collaboration comes into place? How many engineers from IBM versus how many engineers from Toshiba, and how you plan to share the revenue from IP, that sort of thing?
You don't actually, remember what I said, it's pre-competitive. In other words, basic physics, you have to solve the issues without having to get into the question of how do you then deal with it later. As an example, if you're developing high K as one of the alternatives to classic oxide as an insulator, that's just a basic physical endeavor where you have to unpin the Fermi level. And you know, unpinning the Fermi level is a long way from deciding how you're going to compete later in the market. Basically, you don't make that decision. That's why they call it pre-competitive collaboration. We also call it coopetition, right? You cooperate right to the point you got to compete. So as far as the costs go, we just share them, frankly, fairly equitably among us on a fairly flat basis. But you don't do anything beyond that. I mean, we compete head-to-head with many of our partners in the market. A good example, Charter Semiconductor is a fab, right? And we're a fab. We have a foundry process. They have a foundry process. We bid against each other out in the market, and we periodically lose. So be it. But nonetheless, none of us could survive economically viably if we had to pay the whole bill ourselves. So it's a business model where co-opetition has become quite accepted as just how you have to live with it. And it's a really tough mindset. Culturally, that's very difficult. You have to think of the people who are in the fab with you dealing with these fundamental physical problems as your colleagues, even though you're going to go beat the hell out of each other later in the marketplace. So it's a very good question. It's a tough, tough business. Yes?
Is this something that you see as kind of one-to-one cooperation or many-to-many cooperation? That lots of different companies or just you and, say, Charter get together?
It tends to be a many-bodied issue. We actually have, as an example, you know, IBM, Sony, Toshiba, AMD, Chartered, Samsung, Infineon. I mean, it's lots of folks collaborate at our center up in Albany, for instance, and at our research facilities in Yorktown and up where we are in Fishkill. And it actually works. Diversity is a wonderful thing. You know, people, it's very much undervalued, I think. One of the curious things I've found over the years is there are a lot of smart people in the world aside from us being the person who's speaking. And the most amazing thing happens when you take a very, very diverse group of people from very diverse cultures and you put them all in a room with a deadline over their head saying, you're going to ship this transistor with these specs by this date. Engineers are real clever at that point. Doesn't really matter what language you speak. As long as you speak whiteboard, you got it covered, you know? And people basically will wrestle each other for the pen. But it's astonishing how well it works. And in fact, our culture has become remarkable in that there's a company, I won't say which, where when the contract expired, they'd been an ally of ours for so long, just in a handshake. We let all their people stay here. Hell, their kids had been born, you know, locally, and we're going to the local schools for 15 years. We just figured we'll get the contracts out of the way when we're done. And we did. But the fact of the matter is, that kind of a culture where everybody literally assumes you're all part of the same team, even though other parts of your company beat the hell out of each other in the market, is where you have to go. It's a very, very different cultural view of the world, and something you know, we sort of take great pride in, where managers, in fact, in the organization, technical managers and leaders come from other companies than IBM. They actually, many of them are across our technology division leading some of the efforts. They're not really IBMers, but they're part of one team.
So is open source, and in particular the development of XEN Zen, examples of this new way of doing things?
Yeah.
Can you say a little bit about how that worked out?
You know, these are works in progress, but I would say that judging by the success of, a trivial example, of course, is the Linux community, I would argue that ultimately it will be the dominant force in really driving future progress. I mean, it's somewhat of an inevitability to the fact that if you open up enough of the assets you have to the world, people will find, you know, remarkable new things to do with them. If you look at ecosystems, the companies that have been the most successful in many instances are those who've managed in sort of this new regime to develop these very vibrant ecosystems in, nonetheless, an open community. And there are relative amounts to which they're open, right? If you look at ARM, there's a huge ecosystem around ARM, enormous ecosystem of people who know you have access to all of the specs, and you just, there it is, you go do it. Now the question is, you know, then you make it available that you've written code to it, you've done hardware associated with it, it doesn't matter. But it is something where you developed a very healthy ecosystem, and that's been developed around a number of things like Power, where Power.org has, you know, gained traction and people are very steadily beginning to use it, particularly in the embedded space. And Cell will be the same thing. The Cell processor is an astounding achievement for the purposes where you apply it, you know, cleverly. It's not going to be general purpose, but it was never meant to be that way. But for the applications that people have come up with beyond us, it's had some remarkable achievements. Wikipedia, same idea.
One
Yeah.
more over here.
For all this handshake cooperation, I still wonder, how do you get it past the lawyers? Most companies, it seems like the lawyers rule, and they don't usually like this.
I never confuse getting it past a lawyer with it being legal. You always want to make absolutely sure it's legal. Let's just get that one out of the way, you know, for the quotable quotes, right? But the fact of the matter is, I will tell you that our legal department, with whom I've worked closely for many, many, many years, tends to be actually quite extraordinarily reasonable. I mean, they will run it through the litmus test, but at the end of the day, it works fine. Again, what I said is absolutely true. We agree to work on the pre-competitive basic physics in what we do, Because you know what? If you don't have a scientific community, you will die. Okay, I am the worst hardcore advocate of what I call headlights. The basics, the bench scientists, the people who sit there like Bob Denard and scratch their heads for 3 years figuring out how the hell am I going to get one transistor to be a circuit, right, a memory circuit? And then he suddenly solves it, and an entire industry worth hundreds of billions develops. Okay, that comes from basic science, the basic underlying work. Now, it is true that ultimately it becomes a business, and at that point you compete and beat the hell out of each other. But that's completely legal. You are right. You have to be very careful because you don't want to trip over the line where you're conspiring and setting price. All that other nonsense can't occur and doesn't. But the legal community can be absolutely a staunch ally if you take the time to educate them. It's like anything else. If you try to blow past them, that's really unhealthy. I found that does not work well.
If you look at the concept of the long tail, that is a proliferation of smaller volume products, more specialized niches. And if you look at the tendency in our industry for the very expensive cost of development and the cost of mask making, how do we reconcile these two opposing forces to be able to continue to generate new products at a reasonable development cost?
Well, so how do you, new products at a reasonable development cost, first of all, depends upon the term reasonable. It's, how do I say this? I'm not quite sure that I quite understand the gist of the question.
Well, it used to be that developing a chip mask making costs in particular
okay, you're at the absolute
were
cost.
lower, much
Got it.
lower.
Okay.
Now, it costs a whole lot more. The bar for getting a product approved is much higher.
Yeah, okay, so I beg your pardon. Yeah, when you get, for instance, the mass sets on, 0.45, whatever, 45 nanometer, and you're talking about $5 million a mass set, and if you have to make 2 passes, life gets very exciting. Yeah, you're right. It has raised the bar in the fabless community, for instance, enormously. If you're a big enough company, obviously what you do is you run project runs or pilot runs where you basically run 10, 20, 30 die mixed in a single, 20, 30 product in a single die. The shuttle runs of that sort are becoming more common, and people are beginning to deal with it. There used to be, you want to talk about crazed attorneys, there used to be this huge phobic component to doing that because, of course, if I have 30 people's IP up on a single die, there was this nightmare that I would mail your IP to your worst nightmare competitors by accident and end up holding the bag on that one. People are just going to have to get over it, and the controls are going to have to be good enough that we get it under control, and or you sign a document saying, I forgive you. But at some point, you will have to do that. Being very honest, you're absolutely correct. You will have to make an accommodation for the fact that the day of being able to devote an entire run to building your hardware is in peril because of the financials. There's no question. But it can be handled. You just have to be willing to accept a higher level of integration and risk.
Thank you.
Yes, thank you very much, Bernie. That was terrific.
Thank you.